let's start with lecture 3. So, definition. An integral domain A is said to be integrally closed or normal. This is same as saying that it is normal domain or normal if the integral closure of A in its quotient field is A itself. If integral closure of A in its quotient field is A itself. So, of course, you have the natural inclusion, right? A is a subring of the, because A is a domain, so you can talk about its quotient field. So, A is closed, the integral closure of A in QA is A itself. Example, like the example which I have given before, you take Z, take the quotient field which is Q, Z is integrally closed. In fact, the same proof will work for any UFD. In fact, any UFD is integrally closed. So, now the following proposition says that this is a integral closeness is a local property. So, proposition. Yeah, if you see the proof of if Z is integrally closed, same proof will work for this. So, how do you prove Z is integrally closed? You take any element A by B which is integral, where A and B has no common divisor, right? Then you will say that B has to be 1 or minus 1. The same proof will work for two. Okay. So, integral closeness is a local property. So, let A, so I give a number, proposition, this is proposition 4. Let A be an integral domain then following are equivalent. A is integrally closed AP is integrally closed for all P and for all prime ideal AM is integrally closed for all maximal ideal. Proof is easy. You take the A, it is inside your quotient field, call it K. Now, you consider the integral closure of A in K. So, let C denote the integral closure of A in K. So, you have natural, of course, A is integral over A itself. So, you have natural inclusion A to C, and this is a natural homomorphism, right? Now, A is integrally closed means what? That it has to be surjective. So, you call this map phi. So, now you use that if A is under localization, integral close remains integrally closed, and surjectiveness is also a local property, right? If you have a ring homomorphism A to C is surjective if and only if phi is surjective if and only if phi p is surjective for all p. So, this will give P to Cp, and you know the integral closure of AP in the quotient field of AP is nothing but Cp, because localization. You use that fact also, that S inverse. So phi is surjective if and only if phi p is surjective for all p, if and only if phi m is surjective for all m belongs to. So, using these two facts, that then you see that proof follows, right? Okay. So I will write in words that apply surjection is a local property and the previous proposition, which is proposition 3. So, this says that integral closeness is a local property. Okay. Okay. So, now see, when we started integral extension, we started with a ring A, subring A of a ring B, and we talked about what is the integral elements, integral over A, and the set of all integral elements over A, they form a subring. But now you can ask a little bit more. Suppose you take an ideal in A, you can ask elements of B which are integral over not the whole ring A, but the ideal A. So, you consider the set of all ideal. So, what set of all integral elements over this ideal. So, what does it have any structure? Understand? So, next definition. So, let A be a subring of B, and A is an ideal. This is an ideal. So, an element of B is said to be integral over A over the ideal A if it satisfies an equation of integral dependence over A in which all coefficients are from A, except one, except the leading one. Right? The ideal does not have one. Then you say that the element is integral over the ideal A. So now the question is that can you describe such a element, such integral element over the ideal A? So similarly, you can talk about the integral closure of A in B. So the integral closure of A in B are set of all integral elements of B which are integral over the ideal A. So this is the lemma. Let A and B as before, let C be the integral closure of A in B. Let be an ideal and then the integral closure of A in B is the radical of A extension in C. And what is A extension? A extension is in the C. You have this A, C, B. So you have the ideal A. So A extension is nothing but the extension in C. It is nothing but A of C. Extension of A in C, because integral, after all, it should be in C, because C is the integral closure. Right? Proof? So let X belongs to B, integral over A, then you have x to the power n plus a1, x to the power n minus 1 dot 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 a n equal to 0, where ai belongs to A. Right? So now you see that x to the power n, you can write it as minus of a1 x to the power n minus 1 dot 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 plus a n. Right? But a1, a2, a n are in A. So then a1 x to the power n minus 1 plus this, so this element is in A. So this implies that this implies x belongs to the radical of and radical of A extension, because x is the element of C.
Sir, what about the coefficient of x for n?
Coefficient of x to the power n is 1.
I mean, that no need to be.
Now, what is the definition? An element of B is said to be integral over A if it satisfies an equation of integral dependence over A. What does it mean? That means it has to be integral over A. So, when you say integral of A, that means the coefficient of x to the power n is 1. So, it is integral over A plus further that the other coefficients are in script A. Right. So, now you see that these are elements in x to the power n minus, these are all elements in C, right, because x is after all it is an element in C. So, this is in a radical of, so this is a element in A, this is not, this is A extension, sorry, belongs to A extension. So, then x belongs to the, now the what about the converse? So, suppose you take some element in the conversely, suppose x belongs to radical of A extension, which is in the subring C. So, what does it mean? This is in the extension. So, this means that x to the power n is in A extension. So, x to the power n you can write it as summation ai xi, right, with ai belongs to A and xi belongs to C, right. Say I equal to 1 to k or 1 to L. Now, all x1, x2, xn are in C. So, each x1 and each xi's are integral over A, right. Each xi are integral over A. So, now you consider then the module M generated by x1, x2, xl, right. Now, this is a, now x1, x2, xl are integral. So, this is a, so is a finitely generated A module, and this is faithful also. Right. So, this implies if I x to the power n, if I think as a operator on M, it is operating on M. So, this is inside AM, because x to the power n you can write it as linear combination of AI's. So, now you use the determinant trick, or 4 implies 1. So, this will imply that x is integral over A. So, this is so this is proposition 1, 4. So this is a description that when you have integral elements over A, then this has some description. This is an ideal and it forms a right. Okay. Okay. So now I put some obvious statements. So I write it. It sometimes is useful as lemma that suppose A is an ideal in A and B belongs to B, where A is a subring of B. Okay. A is a subring of B and B is integral extension of A. Then following are equivalent. First, B is an B is integral over A over ideal A. B to the power n is integral over A for some n greater than or equal to 1. And B to the power n is in extension of A over B for some B to the power n is in extension of A. So this is obvious, but I just write it. If B is integral over A, then B to the power n is integral over A. Is it clear? Right? And by the previous thing, you see that B to the power n is in. So B is in radical of A. So all these three statements are equivalent. Okay.